Before I do other stuff that are theoretical, let's do something, an application one with exponentials so that you can understand what we're talking about. Typically, exponential distributions are used in modeling lifetimes, and in ecology, it's used in growth curves. It's used in lots of fields, even in physics, radioactive decay, done in algebra, correct? Exponential growth models, decay models. So here we're just throwing in a probabilistic component. Suppose T is the lifetime of an air conditioning unit. Clearly, T is a random variable, correct? Suppose the manufacturer sells you a bunch of AC units. Do you believe that every single AC unit would have the exact same lifetime? No, but they would all have an average lifetime. So here we're saying that T is distributed as an exponential lambda, where the decay over time is about 0.15 per year. And we want to know the probability that the unit lasts for at most 8 years. Earlier I mentioned lambda, or call lambda, as the rate parameter, because that is going to determine how things are going to change over time, over some sort of measurement or unit of measurement. So what are we trying to find? We are trying to find the probability that T is less than or equal to 8. He wasn't even here. He answered it. What the hell? So, and that, in terms of the CDF, I can write it as f of 8. Do we agree? And we know what the CDF is. The CDF is 1 minus e raised minus lambda 0.15 times 8. And what do we get? Huh? 0.6988. It's a 70% chance that it is going to survive or for at most 8 years. But is that beneficial information from the standpoint of a consumer or the manufacturer? No, why not?
Because it could be 1 year.
Because it could be 1 year, right? If someone provided you with this information and said, oh, here is our wonderful AC unit, the probability that its lifetime would be at most 8 years is 70%. Good luck with that. But that would mean it could burn out in 1 year, it could burn out in 2 years, and you would be quite ridiculous to buy that unit. But if I change the question and I said, I want it to last for at least 5 years so that it is a good investment for me. So at least 5 years. Go ahead and find that answer for me. So this is a better question to ask because it helps us understand if our investment is worth it or not. So here we want to find the probability that T is greater than or equal to 5. Whether I put that equal sign or not, it doesn't matter. But this is the complement of the CDF, right?
So the equal sign doesn't matter because it's continuous.
That's correct. So this would be equal to G of 5, right? So G of 5 would simply mean that the survival time is 5 years. So we want to know the probability that the AC would survive for at least 5 years. Now, do you understand as to why we call this the survival function? So G of 5 would simply be, we know G of x is e raised negative lambda x. So e raised negative 0.15 multiplied by 5.
0.4724.
0.4724. If you have this information, if someone told you the probability that the unit would last for at least 5 years is 47.24%, would you spend $12,000 for that particular unit? No, no, right? I could rather toss a coin than buy an AC unit, correct? So the probability is the same. Got to be a very high probability, maybe 90% or 95% here, and sure, what the investor. That's not the case. Good. Now, there are easier ways to make inferences using an exponential also. Let's find the expectation. We don't have to derive it. All I have to do is use the formula. I know lambda is 0.15 per year. So this would be 1 over 0.15. And that would be 100 over 15. $6.6. Right. So clearly, the AC unit on average is going to last for about 6 years, right? 6.67 years. Now, quick information. When we did uniform or binomial, I mentioned or I explained the purpose of standard deviation. It helps us sort of form a range. So here I could find the variance of t using the formula that I have, which is 1 over lambda squared, so 0.15 squared, which is 10,000 over 225. $48. Oh, 44 point what?
4 repeating.
Right, but that is the variance. We want the standard deviation. So what should we do? Take the square root.
It's the 6.6 repeating.
Repeating.
Yes.
See, that's a huge, huge variance, correct? The variability is way too high. So, you know, if we have to do a quick analysis, I might say, well, the average is 6.66. I'll just go one standard deviation on either side, yes. One standard deviation on either side. So I'll subtract 6.66, add 6.66. So 0 and all the way up to
13.3.
13.30, right? So I'll end up saying on average, the lifetime of this AC unit, I mean, this is not the proper way to do it, but a quick way to do it, informal way. is going to be somewhere from 0 all the way up to 13.32. So if you're really, really unlucky, you open it and boom, it's gone. Yes.
Okay, so how is this different from Poisson? Because Poisson was a rate on a given day or just a rate. Also a rate.
Would someone like to answer Mary's question? How is this different from Poisson bounded variable?
Poisson is not continuous discrete.
Very good. Poisson is not continuous.
How
It's-
do you have the question though?
This is a lifetime,
Okay.
right? Lifetime is continuous. Except for the TV channel, I wish that it would just end.
So like, the reason wouldn't be discrete is because it's not gonna necessarily fail on a particular day or week after like you got it. It could be any period. in between,
Right. Yeah, so, because if we made it discrete, we're going to say, okay, it will fail on exactly 1 year, exactly 2 years, exactly 3 years, and so forth. That's not the case with lifetimes. It could happen in a very continuous scale. Do we follow any other? Yes,
It wasn't a coincidence that the mean was the same as the standard deviation.
absolutely. It was coincidence. I didn't expect this, but oh well. Any other questions?
The fact that it's 0.15 doesn't factor into anything, like the fact it's less than 1, that doesn't differentiate between an exponential and a Poisson.
No, that is not going to determine whether the random variable is Poisson or exponential.
Just the wording of the question.
Yeah. And Poisson is a discrete count distribution. Good.